All right, let's dive in. Today, we're taking a huge idea from neuroscience, the free energy principle, and we're going to look at it in a totally new way. We're applying it to the chemistry that existed before life even got started. We're going to explore how some of the very first, most fundamental structures in the universe might have popped into existence not just by random chance, but through some really simple, elegant physics.
So, to really wrap our heads around this, let's start with this simple question. How does a key predict the shape of its lock? I mean, does it think about it? Does it have some kind of goal to open the door?
Well, the answer is it doesn't. At all. A key doesn't think, it doesn't predict, it just fits. Its physical shape is a perfect, passive match for the lock's shape. This one idea, this concept of passive physical fitting, that's the key, no pun intended, for everything we're about to explore.
Okay, so first things first. We have to kind of redefine a word we all think we know, prediction. We need to strip away all the usual baggage that comes with it, brains, intentions, consciousness, and just look at it in a purely physical, structural sense.
And this is absolutely critical. Throughout this whole explainer, I want you to remember we are only talking about a structural analogy. We are not in any way saying that molecules have minds or goals. This is just a really powerful way to understand how stable patterns can emerge from simple physical alignment.
So let's just lay it out side by side so there's no confusion. On one hand, you've got the cognitive prediction that we do with our brains. It's full of thinking, foresight, and goals. And then on the other hand, there's the structural kind we're talking about today. It's all about passive fitting, physical alignment, and just the cold, hard laws of physics.
So how does this simple idea of fitting in become such a powerful principle? Well, it leads us to this amazing concept called surprise minimization. It's a way to explain how stability, how things that last, can emerge from from aligning with your environment.
So here's the big idea boiled down. The free energy principle basically says that any system, whether it's a living cell or a simple chemical structure, stays stable by minimizing surprise. And in this world, surprise is just a fancy word for mismatch. Think of it like a puzzle piece that just doesn't fit, right? That mismatch creates tension, instability. The less mismatch, the less surprise, the more a system is kind of at peace with its world, and the more likely it is to stick around.
Now, when you take this idea and drop it into the world of super early chemistry, it suddenly gets very real. It means the molecular structures that could just naturally handle all the pushing and pulling from their environment, things like heat, pressure, you name it, those are the ones that survived. The ones that couldn't, they just fell apart. It's survival by just going with the flow. Okay, I know this might still feel a little up in the clouds, so let's bring it right down to earth. We're going to look at 3 real-world examples from early chemistry where you can see this principle of passive stability playing out right in front of your eyes.
First up, lipid vesicles. Think of them as these simple little bubbles that were the precursors to our cell membranes. Their entire structure is basically a perfect prediction for living in a watery world. They naturally pull themselves into a sphere to reduce surface tension, they balance the water pressure from the inside and the outside, and they bend in really predictable ways. They fit their environment perfectly without even trying.
Next, let's think about RNA. Why do its chemical bases stack up so perfectly? It's not a choice. You've got these bases just floating around in water, and then simple physical forces, basically water molecules pushing them away while they're weakly attracted to each other, cause them to settle into the most stable, lowest energy configuration possible. A neat little stack. It's a textbook case of a system finding its low surprise state.
And for our last example, let's go way down to the bottom of the ocean, near those hydrothermal vents. The mineral surfaces there act like rigid blueprints. Their repeating crystal patterns literally guide chemical reactions by holding on to certain molecules, keeping them stable, and forcing them down very specific, predictable paths. The chemistry has no choice but to fit the physical template of the mineral.
So what's really cool here is that this principle acts as a kind of bridge. It connects 2 really fundamental things, the inherent patterns that matter itself can form, and the tough, unyielding physical rules of the environment it has to live in.
And there's this fantastic analogy for this, from the economist Herbert Simon, a pair of scissors. Simon argued that to understand something complex, you often have to look at 2 simple forces interacting. You can't cut paper with just one blade, right? You need both working together. So the first blade of our scissors is what the source material calls assembly heuristics. The easiest way to think about this is as matter's own personal toolkit. It's the limited set of repeating shapes and patterns that it just tends to form naturally. It's the list of all the potential things it could become.
Then you've got the fecund blade, and these are the boundary conditions. These are the non-negotiable laws of the universe: temperature, pressure, thermodynamics. This is the hard reality that any potential shape has to deal with. There's no getting around it.
And the cut, that magical moment when a stable thing actually comes into being, that happens right where those two blades meet. A stable structure only forms when one of matter's potential patterns also happens to perfectly and passively fit the non-negotiable rules of its environment. So what you end up with is physics acting as this huge, silent filter. Structures whose shapes align with the flow of energy around them, the ones that fit, they get to remain. But the structures that fight against those flows, the ones that create too much mismatch, too much surprise, well, they're unstable, and they just vanish.
All right, to wrap this up, and this is maybe the most important part, we have to be super clear about what this idea is not saying. We need to put up a few guardrails here to make sure we're all on the same page.
So let's be crystal clear on this. This is just a conceptual framework, a way of thinking. It does not imply that molecules are thinking or have intentions. It doesn't claim this is how life began, and it certainly isn't making any grand statements about metaphysics. It's simply a tool for thinking about how physical forces can select for stable structures. That's it.
You know, if you're going to take one single thing away from all of this, let it be this idea right here. The emergence of stable patterns in our universe isn't just a story about pure random chance. It's a story of alignment. It's a story of structures passively finding a way to fit into the world around them. And that leaves us with a huge, fascinating question to chew on. If this simple principle of alignment, of just fitting in, can help explain how stable structures appeared before life even existed, where else might it apply? Think about it. From ecosystems to economies to social trends, where else do we see complex, stable systems emerge, not from some grand design, but from simply finding the path of least resistance?